Everyone, welcome back. This is Engineer Hussein Mwasapi. So in this video, we'll be looking at a problem under fluid viscosity. So before we begin, do not forget to like and subscribe to the channel. All right, let's get to it. So the question says, a plate having an area of 0.6 meters squared is sliding down the inclined plane at 30 degrees to the horizontal with a velocity of 0.36 meters per second. There is a cushion of fluid 1.8 millimeter thick between the plate and the plate. Find the viscosity of the fluid if the weight of the plate is 280 newtons. Now, how best can we solve this? The first thing we need to do is to create a schematic that will help us understand how the diagram is, or how the question is trying to say. So let's get to the schematics. All right, it says that a plate having an area, so I'll put my data by the side. So we know that the area is given to be 0.6 meters squared. And then we've been told that the plate is sliding down the inclined plane at 30 degrees to the horizontal with a velocity of 0.36 meters per second. So we're having something like this. That is the incline in question. Then let us create the horizontal. This horizontal is fixed to the ground. It's inclined at an angle of 30 degrees. So we have the plate sliding down. So we can draw our plate something roughly as this. So you can call this the plate. So it's sliding down with a velocity u being equal to 0.36 meters per second. Now the question tells us that there is a cushion of fluid 1.8 millimeters thick between the plane and the plate. This incline is the plane in question because it's known as an inclined plane. So there is a fluid in between the inclined plane and the plate. So we can say that this is basically the cushion of fluid. And we've been told that this cushion is about dy having a thickness of 1.8 millimeters. We've been told to find the viscosity of the fluid if we've been given the weight. We know weight is equal to mg, and this is 280 newtons. We know the other data we can create is dy, which has been given in question. We know dy is change in depth, which is the thickness. We know it's y final minus y initial. Every time we have a fixed and one movable part, because in this context, the plate is the one moving, or the inclined plane is the one fixed at an angle. So we're saying y final minus y initial, which basically just gives us the same value. So we say 1.8 minus 0, giving us 1.8 millimeters. Now we need to convert these millimeters to meters. So we say 1.8 just say times 10 to the minus 3, and it will be in meters, because 10 to the minus 3 simply means you're dividing 1.8 by 1,000. So we have our dy. For our du, we know we say velocity final minus velocity initial, or u final minus u initial. And we know that the plate is moving with a velocity of 0.36 0.36 minus 0, giving us just the same 0.36 meters per second. With this information that we have at hand, we can now find means of creating a free body diagram. So this should give us a reasonable free body diagram. The free body diagram will help us know how best the forces acting in this system can be resolved. All right. Every time we have an incline, this is our horizontal. So if we have an incline in this case or this manner, and we have, let's idealize the plate as just a dot symbolizing a particle that is in motion. So we know the angle here is 30 degrees. So this particle, which is the plate, has a weight, and this weight acts downwards. So we know downwards we're having the weight being equal to mg. Now, since the plate is basically at an incline, we need to resolve the weight into its components acting along the x and the y axis. So creating a Cartesian plane, we'll have it in this manner. So basically this becomes our x-axis and this becomes our y-axis. In basic sense, we know that we can create a sign conversion to be this side to be positive, or the other side to be negative, this side positive, the other side negative. So the angle we have here, which is 30 degrees, is the same angle we're going to have here as 30 degrees. Now resolving this tells us to say that we have one component in the y, which is going to be mg cos theta, which is 30 degrees. Then we have another component acting in the x. It will be in that manner, but since the diagram won't allow us to see clearly, I'll make it be pointed in this direction. So we have in the line of action our mg sine theta resolved just like that. So this is how you basically have to resolve the weight into its components. This mg sine theta is the component that is resolved as you are moving towards the weight. In that case, just have to put it here in case you don't have space at the bottom, like in my case here. Now that we know how to resolve this weight, we can continue and clean off our data. Now, in everything we have, we need to remember one thing, that the dynamic viscosity, which is the viscosity in question being asked to be found, is given by mu being equal to shear stress times dy divided by du. Now, in this equation, the only thing we're missing is the shear stress. Now, how best can we find the shear stress? We first need to remember that shear stress is equal to force over area. Now, do we have the force? Do we have the area? Let's see to it that we calculate the area of this particular system that we have. But if you look again, we don't really have to calculate the area because it's given. The area is 0.6 meters squared. So the only thing we need to find is basically the force. Now, what would be the force? So we only consider the direction of motion. So if that is said, then we only consider the force acting in the direction of motion. As you can see here, the plate is going in that direction. So we'll only consider this force component. So in our case, the force on top is mg sine theta divided by the area, which is 0.6. Now remember, mg is weight So we have it as weight sine theta divided by the area, which is 0.6. So shear stress is equal to the weight value that we have is 280. So we'll say 280 times sine theta, which is 30 degrees, divided by the area, 0.6, will give us a shear stress of about 233.33, correct, to 2 decimal places, and this would be newtons per meter squared. So now we have our shear stress. Now, having the shear stress, the next thing we're supposed to do is now plug back in the formula for viscosity. Viscosity is equal to the shear stress that we've just calculated as 233.33 times dy, and our dy value is 1.8 times 10 to the minus 3 in meters. So we say 1.8 times 10 to the minus 3 in meters divided by the velocity, which is du, which is about 0.36, and this gives us a value of 1.17, correct to decimal places, Newton second per meter squared. So that is our dynamic viscosity, or just the viscosity. And if at all we were told to write our answer in poise, we just have to multiply our given answer by 10, and you will have your final answer in poise as 11.67 poise. Remember, if you need to convert Newton second per meter squared to poise, just multiply the answer you have by 10, and you will have your poise value. Alright, thanks for watching. Remember, every time you have an incline and questions involving fluid viscosity, always resolve the weight into its component, or whatever forces that you have into their components, in order to know the particular force acting in the line of motion. Alright, if you have queries, you can reach out to me on WhatsApp on the line +260 77 149 5252. Remember, slow progress is better than no progress. And let's strategize before becoming statistic. Let's try and push for that A+.